Okay, so next we want to talk about how we manage this question of bootstrapping an extremely large matrix, large as in trillions or trillions of cells. How do we do this efficiently without suffering an incredibly long configuration time? And this is where a sort of odd property of the matrix comes into play. On a cell matrix, there is no built-in bootstrap mechanism. There's a pure nearest neighbor connection, there's a single global clock for C-mode operations, and that's it. There's no way to just send in a stream of bits through some pin on a cell matrix chip and have it configure internal cells truth tables. There's no mechanism for that built in. If we want to bootstrap a matrix, first we need to build a bootstrap mechanism. And this might sound kind of odd initially, because a system that you don't even have a configuration mechanism on, why not just include that in there? Well, the reason is that we can tailor the bootstrap system to the specific situation that we're trying to bootstrap into. So if we're trying to build a circuit that's extremely regular, we could build a bootstrap system that will bootstrap this single repeating element in parallel and do a much more efficient job, as opposed to just doing a scan path through a 2D or 3D matrix and configuring cells one at a time. Additionally, being able to configure our own bootstrap system lets us do things like decide how we're going to deal with potential defects or faults in the underlying matrix hardware. So this property of needing to build a bootstrap system before we can actually configure our desired circuit is actually a big benefit of having a self-configurable system, and it's one of the main arguments why self-configurability is so essential for building a system that's going to scale up to trillions or trillions of cells. So how do we do this? How do we configure something in parallel? Well, this is based on the idea of something called a supercell. And a supercell is just a generic term for a collection of individual cell matrix cells that form a larger atomic unit. And we treat this new atomic unit as being a cell, essentially. But instead of just a simple 4-input or 6-input to output mapping, it's a complex block that contains a number of different capabilities, including the ability to do fault testing, to do parallel bootstrapping, to do differentiation in parallel configuration, and to isolate from defective regions. There's no particular definition for a supercell. It can be whatever the application requires it to be. So we're going to look at a very simple case right here. We're going to think of just a single block. So this is our supercell. It's comprised of a number of cell matrix cells. And what we want this to do is transfer configuration information. And so this is going to be sitting in a network of other supercells. We'll talk about how these come into being in a little bit. But we're basically going to send in a configuration stream to this particular supercell. This is the head node of the whole network. We send a configuration stream in here, and one of two things happens. So this stream gets sent out to all other sides, and if it was three-dimensional, it would come out to top and bottom also. And one of two things happen. If there is another supercell sitting on this side, the bits coming out of here are transferred as data into this supercell, which then takes it and transfers it to all sides. The bits coming out here, if there's a supercell down here, those are treated as data, and they're transmitted to all three sides. But if there is no supercell sitting in a region, such as up here, these bits are treated as code, and they're used to configure a region of cells, to bootstrap this small subregion of the matrix to create a new supercell. So what's going to happen is when we send in this one configuration stream, it will get passed in parallel to here and here, but simultaneously this will begin configuring this region of cells up here, and also this region of cells over here, and this region over here, and this region over here, and this region down here. So we begin parallel construction along this perimeter of the previously constructed region. And in this case, we're having 1, 2, 3, 4, 5 cells configured in parallel. But clearly, the bigger this region is that we've already configured, the longer the perimeter is, the more parallel configurations we're going to have in the next time step. That's the basic concept of parallel configuration, and this is an example of something that's called a Medusa circuit. There's a separate lecture set on Medusa circuits, but this is an example of it. It's something that has basically multiple heads to it, and on each of these heads we have a configuration operation going on. Now that's the high level view, but there's some details. The first detail is we usually don't configure cells on more than one side of the collection of elements. The reason being, to do the bootstrapping of this small region requires sending out very specific commands to build wires that will move through here and configure cells. And the commands for doing that to a region on the north are very different for the commands for doing it from a region on the east or to the south. Now we could build additional circuitry inside here to rotate the commands so that if we're configuring to the east, we use the right commands, and if we're configuring to the south, we rotate the truth tables as we're sending them out. You can do that, but it makes this circuitry a lot more complex, and there's no real need for that. So in fact, what we do is we simply take turns as to which side we're going to configure. So our configuration would look as follows. We begin with an initial seed. So this is our first supercell that we just configure from the edge of the matrix, so we have direct access to a few cells here. We use a regular bootstrap sequence and configure this region. And then we send out a command which says configure to the east, and that will configure this region. And then we send a separate sequence out that says configure to the south, and that will configure these in parallel. And then we say configure to the north, and that configures these. And then we say configure to the east again, but this time we have 3 regions being configured in parallel. Configure to the south does 3, configure to the north does 3, and then the next time we say configure to the east, it configures 5 regions in parallel. And so this is super linear. This increases in speed as we run it longer and longer. And basically, on the order of n squared regions will be configured in n time steps. So to build n supercells, it's an order square root of n operation. Now that's for a 2-dimensional system. For a 3-dimensional one, we can extend this into the z-axis, and we actually get an order cube root of n configuration. The other way to look at this, and this is not usually how we do it for certain technical reasons, but the other way to think about this is start off with your region, and let's just first configure this top row. So in our first n time steps, let's assume this is n by n, we configure n supercells in this top row. So n time steps got us n supercells. But in one more time step, in this next time step, each of these supercells configures a region to the south. And now we have 2n supercells, and we got that extra set of n supercells in a single time step. In one more time step, we move from 2n to 3n, and we continue until we've done order n squared time steps, and we've configured order n time steps, and we've configured n squared regions. So it's actually about 2n configuration operations gets us n squared. So this is order square root n. If we want to extend this into the z-axis, we do our 2n configurations to get this n squared plane, but now we change the control signal slightly, and the next time we send in a configuration operation, each of these n squared regions will configure a new supercell above it in the z-axis. So in a single time step, we've gone from n squared supercells to 2 times n squared supercells. In the next time step, it'll be 3n squared, and the next it'll be 4, and after a total of n steps, it'll be a total of n times n squared regions, so a total of n cubed supercells. So on a 3-dimensional region, it's actually order cube root of n. So here we have a case where we want to configure, say, 10 to the 18th supercells. It's going to take us 1,000,000 configuration operations. So 1,000,000 times whatever it takes to configure one of these supercells, and 1,000,000 of those will end up getting 1,000,000 billion, or 10 to the 18th supercells configured. So this is an extremely efficient way to bootstrap a region of the matrix just to create these supercells. Now these supercells are all going to be identical, but we can also differentiate them to some degree as we're configuring, or we can do a post configuration differentiation. And again, remember, in a lot of cases all we're doing is we're laying down a bootstrap mechanism. and we're going to use that to actually load in our desired circuit. But if we tailor our bootstrap mechanism correctly and we set it up, we can configure our target circuit with a high degree of parallelism, and so our final bootstrap time will still be relatively modest. So next lecture, let's take a look at the question of fault handling. Let's just get a very high level view of how we deal with that, and we'll drill down into the details of this a lot more in subsequent lectures, specifically on supercells.